Hello everyone, thank you for joining our online webinar today. My name is Lisa Wang and I am a co-founder and director on the Harvard Undergraduate Clean Energy Group. I'm thrilled to introduce our speaker today, Ms. Enass Abo-Hamed. Enass is the co-founder and CEO at H2GO Power Ltd, an award-winning spin-out company from the University of Cambridge developing energy storage technologies. She has completed her PhD at Cambridge University, where she was a postdoctoral fellow and elected Cambridge University Energy Champion. Currently, she's also a Royal Academy of Engineering Enterprise Fellow and a technology expert consultant to the European Commission. She has 10 years of research and business experience in hydrogen production and storage, catalysis, renewable energy, and energy storage. Enass is passionate about climate entrepreneurship and clean energy technology policy. She often gives keynote speeches at international forums and participates at high-impact roundtable discussions on clean energy, energy security, and women entrepreneurship in technology. So today, Enass will be speaking on energy poverty and the gap that clean energy and energy storage can bridge for millions in the world. She will highlight the role of companies like hers, H2GO Power, in addressing climate change, using zero-emission solutions and focusing on hydrogen, and her company's latest innovation on decarbonizing air travel. Without further ado, Enass, take it away.
Thank you very much, Lisa, for the lovely introduction. So, hello everyone. Thank you very much for joining us today to this webinar. Today I'll be speaking to you about H2GO Power, the company I started when I was a student like you. I was a PhD student back then, and my PhD was around hydrogen storage and catalysis. Throughout the second or third year of my PhD, basically I had a patent where I wasn't sure what the technology was good for. So within a students group, basically, we started to look at where this could fit, why this could be a good solution. And after talking to industry companies, we basically felt that there must be something that we could do with it. We decided to start the company when we realized that there was an energy poverty gap in the world. And that was 2015, I think, when I went on a trip to Africa and I saw firsthand what energy poverty means. So as of today, there are 1.2 billion people around the world without access to electricity for basic services like cooking, studying, and medical treatment. And this urgency increases dependency on emitting and polluting fuels, diesel and kerosene. And moreover, climate change hits vulnerable communities in the developing world the most. And until that trip to Africa, I honestly, which is 2015, we're talking about 5 years from now, I really did not know what energy poverty means. I realized on that trip that doing a PhD that is related to very sophisticated technical solutions or giving talks isn't probably going to impact an issue like that as much as if there was a way to look at building a product that you could introduce to vulnerable communities in the developing world who suffer from not having access to basic services, whereby even if they did not understand the technical depth of how the product worked, they could use it. And that is where all the impact that I wanted to make as a scientist. Now, having started from this slide and this in this story. The good news is that in the developing world, there is an impressive adoption to renewable energy. And by 2040, we will probably add 60% of the the added energy capacity in the world. That would come from renewable energy, which is quite impressive, including the developing world. That means that by 2040, you probably won't have any energy generation issues, but we will probably have energy storage crisis because of the nature of the intermittence of renewable energy, whereby you're dependent on the weather, on when the sun shines and the wind blows, and they don't they don't have a very regular repetitive pattern. It's intermittent. Therefore, you really need to counter energy generation with storage. And although even if we're increasing a renewable energy and clean energy in our mix, to work towards a robust transition plan, energy storage have to be at the center of that plan to make the solution reliable and sustainable. My specialty is in hydrogen, and I personally think that hydrogen is the transformer in the energy transition. So hydrogen is the smallest molecule in the world, and it doesn't have any carbon to start with. So when you burn it, to extract energy as an energy carrier, when you burn it or electrochemically convert it, you don't produce carbon emissions as an output, but you do have an energy output. And that elegance in that solution, whereby we're talking about energy dense, no carbon, and a carrier that could store energy for long duration like no other candidate. These components basically make hydrogen a very interesting and leading candidate in the energy transition aspiration plan that we have. So we started to talk about energy storage as of today, and in the future as well. We won't have one energy storage solution. We will have a portfolio of solutions. Some of them are very good solution for very specific tasks, but they wouldn't work for other tasks. For example, if we're looking at capacity and scale, what supercapacitors could do, hydrogen might not be positioned very well to do. And if we wanted to store energy, for example, for really long durations, for a month, lithium-ion batteries are not a good candidate for that because they have technical limitations. Or other solutions like pumped hydro, which work at scale extremely well, could store energy for long durations. However, there are geographical constraints around that. So therefore, the energy storage, there isn't one energy storage solution. There are multiple, and it's extremely important to design whatever system we have, whatever solution we use, based on the constraint that we have in a local area. However, if you look at the figure on the left-hand side of the slide, one thing that is very interesting, the fact is hydrogen actually covers the discharge duration, the storage duration, best than most of the other solution. And it works quite well at scale as a candidate. One additional thing that I'd like to say on this slide is basically what could we use hydrogen or where could we use hydrogen to cover for the final energy demand. On the right side of the slide, basically that figure looks at ambitious scenario that for a study that was done in Europe, and it only covers Europe, that by 2050, if we wanted to implement using hydrogen for different applications like buffering in transportation, heating and power for buildings, looking at a new industry and existing industry feedstock. And if we add up all these possibilities and applications on an ambitious scenario, we could cover around quarter of the energy demand in Europe. And that is quite an impressive scenario to work around because of the decarbonization impact and reaching them fast. So I'd only like to talk about the ambitious scenario just because I really believe that this is where we should be focused. The business as usual might not be enough even by 2050. Moving on from that slide, I'd like to introduce what we do as in designing a product that could cover the gap of storage. So basically at H2GO Power, the company that I started with colleagues back in Cambridge, look at two products. One of them is plug and play storage systems, whereby we store energy in the form of hydrogen for long duration. It's effectively a hydrogen battery that takes power in that comes from renewable energy, wind or solar, and then basically that power goes into a box, a power box, that includes three compartments. One of them is an electrolyzer that basically take the power that came in and water, split that water into hydrogen and store the energy as hydrogen for as long as it's needed. And only when the demand of the user peaks at the other side, that hydrogen then gets released into a fuel cell and converted to energy. This could power grid applications or other applications that are off the grid. There is a management system that we're also building to best power and manage these systems, whereby we're developing AI algorithms and systems that could basically predict the demand of the user, predict when the weather is at a point or when the generation assets are at a point that are generating excess energy, where the price point is either zero or sub-zero, which is the best time to store energy. And when the demand is at peak, then you release it, and then the price could basically match the demand. And we are working to start implementing, building these systems in a remote island in Scotland, in Orkneys. The scale that we're looking at is 1.5 megawatt hour scale, which is large commercial scale, and whereby we will basically link these units to wind turbines, and then the power that is generated will be tested by pumping it back to the grid or for a different off-grid application. So there is an important point to bring up here on the cost. So the units that I've presented are energy storage units. So basically on the value, they deliver a similar value as a typical lithium-ion batteries, whereby they are storing energy, although with different capabilities, but the cost comparison is extremely important because introducing a new product to the market will have to be somehow, even if it's not competitive at an entrance point, it will have to be competitive at scale to be widely adopted. Otherwise, it will be very difficult because the consumer, at the end of the day, as much as they would want a product that fills the gap that they have, cost will always be the driver to adopting a technology. So looking at the cost comparison between lithium-ion batteries and H2GO unit, whereby we're looking at a 2.5 megawatt hour scale. So for a typical cost for lithium ion is $273 per kilowatt hour, whereby ours is 243. So the capex cost is pretty close. It's a little bit lower, but not significantly lower. And that's where I think the competition isn't significant. However, what distinguishes our solution, in addition to the to other superior technical performance parameters, is the levelized cost of energy storage. If we look at when you are looking to deploy a system like that, for how long you'd like to deploy it, and what are the technical limitations of lithium-ion batteries, one of them is the lifetime of the battery and the number of cycles that the battery could do. So our systems can last for 3 times they can have a triple lifetime at least, and they could last for 18 years. And when we calculate the cost over the lifetime of the asset, it could be third. And I think this is the important distinguishing point for pricing of a technology like ours versus lithium-ion batteries. In addition to the storage capacity per unit volume, ours could do around 2.2 times more energy, more capacity per unit volume, which means you would need to rent less land to store the same amount of energy or more energy. And if we add up all these advantages, this is where the competition could be and the comparison could be. Just to look at a use case, moving back to the developing world and where a solution like that could be beneficial in the developing world. Basically, if we look at a plug and play power unit that could be connected close to a user where you have already installed solar panel. So let's look at a case in Nigeria whereby we looked at a hospital site, and with 1 unit of our solutions, the site owner could cut up to 30% on the energy bill, and importantly have 64% reduction in their CO2 emissions because of the replacement from diesel. And importantly, have a reliable supply of power for 24 hours 7 without having to deal with expensive diesel at peak times or any blackouts that they experience. That means the hospital could possibly run smoothly and increase their operation capacity just because of their ability to have regular access to power that is reliable. Um, on the other hand, so that's it for now. With the plug and play energy storage systems, this is one product that the company is developing, and we have a second product that we have developed, which is power for drones. It uses exactly the same core technology, which is storing hydrogen at low pressures without having to compress hydrogen up to high pressures. So, for example, hydrogen tanks that fuel fuel cell cars, as of today, they run on 700 bars, whereas our technology works at a pressure range of 1 to 10 bars. So this is less than the pressure in your coffee machine. And we do that by converting hydrogen into a solid state, by allowing transitioning to a different state of the matter through absorption in chemicals. We can do that. So we don't store hydrogen as gas, we store it in solid state in a chemical form. So with the power for drones, we use the same core technology, but we manufacture our reactors very differently. So we 3D print the reactors, and the internal structure of the reactor is designed to manage heat in and out of the system, whereby when hydrogen come into the reactor, it will need to be stored at ambient temperature. And when we want to release it to a fuel cell to keep the drone going, we have to heat the medium in a very smart and controlled way. And that is supposed to be a behavior that matches the needs of the fuel cell. And with our proprietary technology, we're able to do that. And because of the 3D printing, basically we can print in shapes and structures that suits the drone that we want to put this system on. And importantly, the main benefit is that these systems are light enough and can store enough energy to keep drones flying longer. And the comparison with typical lithium-ion batteries is 3 times. So 3 times longer flight than typical lithium-ion batteries. And that's an important advantage, because if we look at the attention that we have around drones these days, and versus time and the time that it takes to develop and mature this technology, basically mail and package delivery is at the top of the curve. In terms of interest in delivery of mail packages or Amazon packages, for example, it could be a lot more efficient, and we could get deliveries faster if we had drones that were operationally more efficient and less costly than humans. And this is one of the things that we really aspire, that one of the applications that we really aspire to be involved in, because of the flight time capability. You don't want to send a drone somewhere and not be able to get it back because it runs out of battery and it's going to take time to charge it. And there are multiple other applications like crop monitoring or agriculture, whereby a solution like that allows longer flights could solve a problem that would increase productivity in the field. And importantly, an application that we're really interested in is the eVTOLs and flying taxis, for example, whereby if you want to fly longer, you need to use a bigger battery, and that means a heavier system. And weight is very important when you're talking about things that fly. Just because you want less weight for power and more weight for other things. If you are taking people on board, they are going to come with a weight. And the more people you want to have, that means the less weight for the power you could really put on that system. And with a solution like that, because of its light nature and controlled manufacture, this is a differentiation and advantage that we hope to develop up to that scale within the next few years. And I think this brings me to the last slide of my presentation. These are pictures from a successful pilot flights that we did actually in Boston last year with a fuel cell company called Ballard. And we were able from the first attempt to basically get a large drone to fly with this our system, and that was an important milestone in our development. And it's just important to acknowledge that this work has been ongoing for the past 5 years, and without the faces on the slide, it wouldn't have been possible to get this far. And there's still quite a lot of work to do. So hopefully there will be more and more faces on the acknowledgement slide in the next few months and years as we grow and scale. And with that, I'd like to stop here and maybe give you the stage to ask any questions that you're interested in, and I will expand on any area I mentioned based on your interest.
Fantastic. Thank you so much, Enass, for such an informative presentation. I personally really enjoyed learning more about hydrogen and energy storage and its role in really transforming a lot of different industries. So yeah, if anyone wants to kick off the Q&A session, feel free to either unmute yourself and ask a question, or simply type in your question into the Zoom group chat.
Yeah, sure. I'll ask a question that I was thinking about. So firstly, yeah, thank you so much for the presentation. Really enjoyed it. I was just wondering, in the section where you were talking about technologies used for like UAVs and drones, has there been any discussion in using that same technologies on like with like expanding it for electrical vehicles? And if so, what sort of technological barriers do you guys face in expanding that to kind of accommodate larger vehicles?
So basically, this technology has not yet been considered for electric vehicles, for the simple reason of, so these systems, what I presented, the two products that we're working on is a stationary system or a drone. because when you turn these systems on, you want them to run for as long as possible. And this suits very well stationary applications and a drone, right? When you turn it on, you want to keep it in the sky flying for as long as you can. With cars, because of their movement pattern, which is move, stop, with every cycle of moving and stopping, you have to heat and cool to extract the hydrogen. That has an element of inefficiency that needs to be customized and designed just for that pattern of movement. And we haven't seen so far that this could be like the solution that we have could be best positioned to address that yet, and it would need a bit of development just for that market. So when the market matures enough, it might be a more suitable time to look at that. At the moment, there is a thirst for solutions like that for drones and stationary applications. And they work quite well on both. So this is why we focused on them and not on mobility.
Perfect, thank you.
Do we have any more questions?
Yeah, I'll jump in. So you talked about some of the applications for hydrogen-powered UAVs to kind of compete with delivery services and increase efficiency in this field. So when do you believe that this technology will be economically viable, and how do they currently compare with delivery costs for other services?
That's a really good question. So obviously, as we develop technologies like that, and others work on them as well, and hydrogen fuel cells on drones, I mean, the benefits of these in terms of longer flight time, that has been proven by others, not necessarily by us. We've done it safer, and we've manufactured it differently. So we will need to go through a few cycles, a few generations of improving the product to a point where it's certified and we can sell it in the market. And I expect that's going to take. So we hope to launch our second trial in 12 months, and from that point we'll go to certification and then selling in the market. In terms of cost competitiveness, because we 3D print and we won't be manufacturing at scale, at least at the beginning, it is already cost competitive with lithium-ion battery at the 3D printing and assembling point. It could be reduced later in the future if the cost of the manufacturing goes down. But I think the important bit here is to look at the value rather than the costs, because longer flight time is a killer value for an application, whereby the customer would be willing to pay for it, for the advantage, even if it was more expensive than a counterpart, a lithium-ion battery solution.
Great, thank you.
Hi, thanks again for your wonderful presentation. I know you talked about earlier how the developing world takes up renewable energy like fairly easily. How do you see like the developed world, who's already really dependent on non-renewable energy, like taking up technologies like this?
There's definitely space for technologies like this in both worlds, because although we do have, say in Europe, we do have reliable grids, but we have to decarbonize. The pressure on government to look at alternative and to increase the adoption of renewable energy will force us to look at, because of the intermittency of renewables, will force us to look at solutions like this and integrate more energy storage as we integrate more renewable energy. So there is different type of pressure on both worlds to change.
Thank you.
Sure.
Something that you described earlier with your technology with H2GO Power that I found really exciting was how you're able to store it in, you mentioned like converting it to a solid state in order to increase energy density of your storage format, and you're able to maintain very low pressure as a result. So could you speak a little bit more about this and how that works?
Yeah, so basically that process means that we are replacing the conventional method of compressing hydrogen up to high pressures, because hydrogen is a happy gas, in order to store enough of it in a certain volume. You just have to compress because it wants to be everywhere. Now, to avoid doing that, we use a chemical process of conversion. So we use metal materials that have chemical properties that allows absorption of hydrogen on the surface of the metal powder. And by that process, what happens is that the hydrogen bond gets broken, and then a hydrogen metal bond gets formed, and this is the storage stage. And when you want to release hydrogen, you'll need to convert it back into gas. So you need to break the hydrogen metal bond by introducing heating to the system. And then the hydrogen molecule reforms, and then you release it as gas to the fuel cell for conversion. So this is a process, the chemical process that we did not invent. What we have invented in this process is how you manage the heat for the point when you want to release, when you know that this is the time to release hydrogen because the user is going to need it. How do you manage the heat throughout the reactor where you're storing a lot of material that is absorbing a lot of hydrogen? And with that, we managed to store twice the volume of hydrogen in the same space, as opposed to hydrogen stored at 700 bars. And I think this is one of the really unique points that we have in that storage system. Do you have any more questions?
I guess I'll jump in again. Again, that was such an interesting presentation. So many questions came to mind. Could you speak a bit about kind of the transition and like current landscape of hydrogen development over the last few years, and kind of if you've seen a lot of growth and what areas specifically have enabled this growth and more rapid development or adoption of hydrogen storage?
So when we started the company 5 years ago, at the very beginning, we had discouraging feedback on actually doing it. The interest in hydrogen was not that strong. People just didn't see the potential of it. And I think what happened in 2015, which was the Paris Agreement and the pressure to decarbonize and look at the 2-degree scenario, really pushed governments to think about how they could introduce pressure to decarbonize operations around highly emitting industries and services. And in addition to that, Toyota put the first hydrogen fuel cell car on the road, and they started to mass manufacture them because for mobility, hydrogen fuel cell is a fantastic solution to decarbonize and give you the range that lithium-ion batteries won't be able to do, the technical limitations. And I really think that because we want to clean up the air in cities and decarbonize, the pressure on governments to do something about that, plus looking at the commercial and industrial emissions, has driven many industries and governments to look at developing hydrogen strategies. And the momentum in the past 2 years has been, it way exceeded our expectations when we started the company. So basically we've seen in the past 5 years, we've seen like a significant shift from not much interest because what we had was good enough and was at a good price point, to a huge amount of interest and momentum in introducing new hydrogen solutions into the market.
It's really great to hear about that momentum. I know you're based in the UK, so you might be more familiar with the European landscape, but do you think that the similar momentum will be seen across the world and also in North America, or is that accelerated transition already happening?
Yeah, so California, for example, is one of the leaders in the world in ruling out hydrogen stations for fueling, and they have a quite impressive pace for doing that. However, the rest of the US is still behind on that front, and Europe as well is considered as a leader. Because decarbonization is quite important, whereas policies elsewhere are not, might not be top priority, or might not be top of the list. China as well is adopting hydrogen solutions in impressive pace, because of the air pollution issues and progressive policies around decarbonizations. Australia, because of the demand for reliable source of power and moving away from coal as well, the pace of adoption and wanting to implement a large-scale hydrogen project is quite impressive. It really is different in different places in the world. Some have decarbonization and moving away from coal at the top of the list, and some feel that climate change isn't a big threat and decarbonization might not need to be a big priority on the government's agenda. And that affects basically the adoption and the market expansion and growth. Are there any other questions or points that you'd like to hear about around our development plans?
I guess if there are no further questions about your development, I would love to hear about kind of your experience working in this field, and what was the greatest challenge that you had to overcome, and kind of now that you're able to like reflect on overcoming these obstacles, what lessons would you love to share?
That's a good question, very, very good question. So basically, when we started, we were students, and we had no experience, and we were very naive in terms of our expectations from the industry in this particular field. And after starting the company and wanting to make progress and to hit our milestones and grow, the largest challenge was really being able to develop fast enough and raise funding from investors and from the industry who saw that this is a priority or a company that could really affect the the energy transition and the energy industry. The energy industry is very regulated. It moves at a very slow pace. Any new product you want to introduce to the market takes, especially if it's a technology solution, takes years to build, develop, test, certify. And the appetite of investors or for potential strategic partners is not that high for this type of products. It's much higher for software-based solutions where the cycle of developing them is very short, and the cycle of monetizing them and marketing them as well is very short until you get to the point where you are generating returns. And that was extremely challenging because we felt that we started the company wanting to make impact, and it didn't feel in many places that that we were synchronized with the industry and with the investor world. And it took some time to get to a point where we could prove our credibility, prove the differentiations on what we have achieved, and how we could really carve a space for ourselves and position our technology in the market. That has been quite challenging, and it took some time. It took many years to make progress. And what we've learned was that someone has to do this. It didn't make sense that all the or a big part of the funding and the startups are around software solutions. In the energy industry, it's based around a hardware product. Someone has to do it. And I really think that the lesson learned from that is something that I would want to try and pass it on, and try and influence people to do more of that, because it's really needed. And if we are going to push towards energy transition and we really want to make an impact on decarbonization, startups with help of government could do a lot, whereby incumbents and oil and gas industries would have less of an interest to develop competitive solutions to what they already do. So someone else will have to do it.
That's a really great takeaway and very motivating, again, for kind of entering an emerging industry that has so much potential for innovation.
Yeah, thank you very much for asking me to talk about my experience and give a little bit of an insight into what we're building at H2GO Power. I did not want to expand too much in one direction because I really wanted to have more input from what interests the students and the group, the audience who join us. So if you have any point of interest or a question, feel free to get in touch with me even after the webinar.
Wonderful. If there are no further questions, I would like to wrap up this webinar by thanking Ms. Enass once again for sharing her insights and knowledge in accelerating hydrogen and energy storage. Thank you everyone for joining us on this webinar, and I hope you enjoyed it.
Thank you very much.
Thanks so much.